In the past, we found that we can usually get away with sending at a T1 rate for short periods. In addition, we want to send traffic to the interface every 10 milliseconds instead of every 125. Here is the map class that will implement these policies. The interval at which bytes are sent to the interface has an effect on delay and jitter. Though the iOS syntax options appear to allow TC to be set directly, it doesn't actually work. To set TC, you set committed burst, or BC. The fraction of BC over CIR results in TC. Note that the excess burst value, BE, is the difference in bits per second between our CIR and our peak rate of 1,536,000. The excess burst value comes into play when we have been sending below CIR for a time. Every byte that we could have sent but did not is credited to excess burst. The min CIR value is our PVC. Because we have enabled adaptive shaping based on beckons, our router will reduce its sending rate when the provider is congested. We have paid for a guaranteed PVC of 384K. The min CIR sets a floor below which we will not throttle. Next, we'll apply our map class to delc102 and observe the result. Note the sustained bits per interval is 5,120 bits, or 640 bytes. This is our committed burst. Our byte limit is 128,640. This is the 640 bytes from the sustained rate, plus 128,000 bytes of excess burst. Note that we are not actually permitted to send this byte limit every 10 millisecond interval. The excess burst is spread over the interval of 1 full second, so the byte limit figure is not very meaningful when excess burst is configured. There are 4 map class options related to FRTS on DTE interfaces that we have yet to mention. They are feckin adapt, hold queue, TC, and traffic rate. Feckin stands for Forward Explicit Congestion Notification. This feature works with beckon, backward explicit congestion notification, to get senders to throttle back during congestion. When frame relay switches are congested, they can set the beckon bit in the Q922 header. When the feckin adapt is configured on the receiving router, it can set the feckin bit in the header in frames destined back to the sending router. If the sending router has adaptive shaping beckon configured, it will throttle its sending rate back. The hold queue map class command controls the size of the shaping buffer. It is 40 packets deep by default. It can be configured between 1 byte and 1024. The presence of the TC command in map class configuration mode suggests that the shaping interval can be set directly. This is not the case. The documentation says it should be used to set the TC when the CIR is 0, but we have not yet seen this work. For data traffic, it is best to let the router scale TC automatically based on CIR. If you need to set TC, it must be done indirectly by setting the committed burst. The traffic rate command is an alternate syntax for setting the CIR and the excess burst. In our earlier example, we set CIR to 512K and the maximum rate to T1, or 1536K. There, we set the BE value to 1024K, the difference between 1536 and 512. The traffic rate syntax allows us to set CIR and EIR, excess information rate. EIR is the peak rate. Here is how it would be configured in iOS. The traffic rate command simplifies the excess burst calculation, but it is not well documented. It does not permit the specification of TC, and we do not recommend it at this time. In order to demonstrate traffic shaping, we have a traffic generator sending a stream of UDP packets to R1 and then across the frame relay connection to the loopback on R2. This stream averages 64 kilobits per second, but it varies randomly between about 56K and 72K. To simulate an access rate mismatch, we have configured the clock rate on FRS port S1 to 64K. This is the output port for traffic from R1 to R2. We have changed the port buffer size to 5 packets from the default 64 packets. First, let's see what's happening on port S1 of FRS. Note that there are currently no packets in the queue, but since the last clearing of the interface counters, a total of 145 packets have been dropped because the 5-packet buffer has overflowed. Let's take another look at this interface. We'll simply repeat the show command. Up now we've dropped 183 packets. 183. Up to 190, and right now we see that there are 4 packets currently in the 5-packet buffer. Since our traffic average is 64K and the clock rate is 64K, we may be able to keep the frame relay switch from buffering and dropping packets by implementing frame relay traffic shaping R1. First, we create a simple map class with a CIR of 64K. We then enable frame relay traffic shaping on interface S00 and apply the class to del C102. Now we'll go back to FRS, clear the counters, and observe the buffer on S1. Note that we have 1 packet in our buffer, but we haven't dropped any. Let's take a look at this a couple more times. We have 3 packets, but we still haven't dropped any. 1 packet, 1 packet, no packets, the buffer's been cleaned out, so the frame relay switch is no longer dropping packets. Let's go back to R1 now and see what's happening there. The command show frame relay PVC 102 will show us the shaping details. Note the CIR of 64,000. The committed burst is also shown equal to the CIR. However, the byte limit is 1,000 bytes, as you see here, and the interval is 125 milliseconds, or 1/8 of a second. The committed burst is actually 8,000 bits per second. It is shown as 64,000 because we did not set it explicitly. Instead, we relied on the router to scale the interval. You see the default min CIR is 32,000 bits per second. It is half the CIR by default. Note that it says shaping inactive. This means that there are currently no packets waiting in the buffer. The output queue line gives us the details of this buffer. Note that a total of 34 packets have been dropped. Let's see how this buffer behaves as the traffic rate varies over time. This will give us the output for show PVC 102 for just the output queue line. Notice there are still no packets in the buffer, but we've dropped a total of 39. So the traffic rate at the moment is below 64,000 bits per second. We'll just keep an eye on this by hitting the up arrow and observing the result. Still no packets in the buffer. Now you see there are 7 packets in the buffer. The full showFrame-PVC-102 command would show shaping active at this point. The buffer has increased to 15 packets, so we appear to be at a peak above 64,000. Traffic is still increasing. We now have 28 packets in the buffer. Now we're up to 39, and you can see we're starting to drop more packets. The buffer is now shown full, and since the last clearing of the counters, we've dropped a total of 59 packets. Is there anything we can do to avoid these drops? Well, let's increase the size of the hold queue to the maximum 1,024 packets. And we'll repeat our show command. Notice our queue is now 1,024 packets rather than the default 40. It would take a very long traffic burst to fill this queue. The problem with this solution, however, is that it takes a long time to empty such a deep queue. Packets will suffer very long delay and jitter times. This is the trade-off for fewer drops. In this presentation, we discussed and demonstrated how FRTS could be useful in a traffic rate mismatch situation. In a later presentation, we'll demonstrate some of the advantages of class-based frame relay traffic shaping. When we discuss voice over IP over frame relay, we'll see how FRTS and class-based techniques can be combined to improve voice quality over frame relay.